Have you ever just stopped and stared at a towering mountain, a massive canyon, or even a simple curve in a river and wondered, how on earth did that actually get there? Well, if you have, you are in exactly the right place. Welcome to today's Explainer. This is our master guide where we are breaking down complete geomorphology. We're going to explore the ultimate sculptor, which is, of course, our own planet. We'll uncover exactly how the Earth is dynamically built up and then continuously destroyed, quite literally from the inside out.
To really wrap our heads around what the Earth is doing today, we kind of have to rewind the clock and look at its past. Our geological timeline starts way back in the Azoic era. This was an entirely lifeless, fossil-free period dominated by primary rocks, like granite. From there, we shift into the Paleozoic, or primary era, which is where life finally takes hold in these warm seas, with the first invertebrates. Fast forward to the Mesozoic, the secondary era, which is famously ruled by the reptiles. And finally, we arrive at our current block of time, the Cenozoic. This is the era of mammals, and it's also when modern, massive structures like the Himalayas were actually formed. It's an epic journey, honestly, of both biological and geological evolution.
Okay, so here is our roadmap for the explainer. 1. Inside the Earth's layers. 2. The shifting tectonic plates. 3. Earthquakes and volcanoes. 4. Evolving landscape theories. And finally, 5. Nature's sculpted landforms. Let's dive right in. Section 1. Inside the Earth's layers. To understand the surface we live on, we first have to crack the planet open and see what raw materials actually make up its internal engine. So, cracking open the Earth reveals 3 really distinct chemical layers. Starting right at the top, we have the crust. Geologically, this is known as SIAL because it's packed with lighter silica and aluminum. Then, right beneath that is the mantle, or SIMA, which is made of much denser silica and magnesium. And finally, sitting at the very center of it all, we hit the core, or NIFE, made of incredibly heavy nickel and iron. The big takeaway here is the simple but absolute rule. The Earth gets significantly denser the deeper you go. Now, you might be wondering, and it's a completely fair question, with all these varying densities, how does the planet balance it all? Like, why don't towering mountain ranges like the Himalayas just tip the spinning Earth right over? The answer is isostasy. Basically, it's the mechanical balance maintained between Earth's elevated land masses and its really deep ocean basins. Scholars like Airy and Pratt debated the exact mechanics of this for a long time, but the core concept is essentially a balancing act. Think of it like a giant iceberg. A massive mountain peaking up on the surface actually requires a deep, lighter root beneath it to stay afloat in that denser mantle. Section 2. The shifting tectonic plates. Now that we know what's inside and how it all balances out, let's see how those immense internal forces push the surface around. You know, the map of the world hasn't always looked the way it does today. Building on Alfred Wegener's groundbreaking continental drift theory, the whole story basically starts with Pangaea, one single massive supercontinent. But around the Carboniferous period, this supercontinent was literally ripped apart, splitting into Laurasia up in the north and Gondwanaland down in the south. So how exactly did that happen? Well, it was driven by thermal convection currents deep down in the mantle and a process called seafloor spreading, where brand new crust is created at mid-ocean ridges. This mechanism drove our continents to their current positions at roughly the same speed your fingernails grow. Pretty wild, right? So the Earth's crust isn't just one solid shell. It's cracked into puzzle pieces that we call tectonic plates. And what happens at their borders is a fascinating study in contrasts. When these plates meet at convergent boundaries, they violently collide. The heavier oceanic plate sinks or subducts, causing a ton of crustal destruction, creating deep ocean trenches and pushing up massive fold mountains. On the flip side, we have divergent boundaries. This is where plates pull apart, quietly allowing magma to rise up and construct brand new crust. So basically, one boundary type violently destroys, while the other quietly builds. And all this tectonic movement acts like a giant recycling center for the building blocks of our planet, rocks. There are 3 main types we need to talk about. First, igneous rocks. These are our primary rocks. They form directly from cooling magma or lava. You can think of them as the parents of all the other rocks. Then we have sedimentary rocks. These form from the slow erosion, deposition, and layering of older rocks over time. Crucially, because they are layered over millions and millions of years, they're the ones holding our planet's entire fossil record. Finally, metamorphic rocks. These are existing rocks that have been baked and squeezed by the extreme heat and pressure of tectonic movements, which fundamentally changes their whole chemical structure. Section 3. Earthquakes and volcanoes.
What happens when these massive, shifting plates get stuck and finally snap? The results are incredibly sudden and often catastrophic. When a plate snaps, it releases a massive amount of energy in the form of seismic waves. And actually analyzing how these waves travel is exactly how scientists figured out what the inside of the Earth looks like. First up, we have P waves, or primary waves. They are incredibly fast, push-pull waves that can travel through both solid rock and liquid magma. Next are S waves, or secondary waves. These are transverse waves, and here is the key thing. They cannot travel through liquids. The fact that S waves just stop dead at the Earth's outer core is exactly how we know that layer is molten liquid. Finally, we have L waves. These are the surface waves. They travel right along the crust, and unfortunately for us, they are by far the most violent and destructive to our cities and infrastructure. And as you might guess, alongside the shaking comes the fire. A staggering 80% of all volcanic eruptions happen at destructive convergent plate boundaries. When that dense oceanic crust gets shoved deep into the mantle, the immense friction and heat cause it to melt. This newly formed, highly pressurized magma eventually bursts right to the surface, fueling explosive volcanic eruptions. This is exactly why the shores of the Pacific Ocean, where plates are constantly colliding, are famously known as the Ring of Fire. Section 4. Evolving Landscape Theories. Okay, we have our continents, our mountains, and our rocks. But how do they evolve over millions of years into the specific hills and valleys that we actually live on? For a really long time, people thought the Earth's features were just created instantly by sudden, massive catastrophes. But then, scholars like James Hutton came along and proposed a totally revolutionary concept called Uniformitarianism. His famous quote, "Present is the key to the past," changed the whole game. Basically, it means that the exact same slow, everyday processes we see outside our windows today, like rain washing away a little bit of dirt or a river slowly carving into a bank, have been operating steadily since the Earth's very beginning. Given millions of years, those tiny, uniform actions are more than powerful enough to sculpt massive mountain ranges. This realization sparked a truly fascinating academic debate about how landscapes age. On one side, we have W.M. Davis. He argued for a really predictable, time-dependent cycle of erosion. Just like a person, he said a landscape goes through a youth stage with sharp, jagged mountains, a mature stage of softening, rolling slopes, and an old age stage where it's just worn down to a flat plain. On the other side of the aisle, Walther Penck argued against that simple timeline. He believed landscape evolution is a time-independent morphological system. To Penck, it's not a timeline. It's a constant mathematical battle between the rate at which the land is pushed up by tectonic forces and the rate at which it's eroded back down. Regardless of whose theory you lean toward, the actual degradation of the landscape happens in 3 distinct, relentless steps. Step 1 is weathering. This is the mechanical or chemical breaking down of rock right where it sits, often just from temperature changes or water seeping in. Step 2 is mass movement. This is gravity doing its job, literally pulling that newly weakened debris down the slopes, think landslides or even just slow soil creep. Finally, step 3 is erosion and deposition. Dynamic agents like rivers and wind sweep in, transport those broken materials away, and eventually deposit them in a brand new location. In fact, that's exactly how the dirt sitting in your backyard might have originated hundreds of miles away. Section 5. Nature's Sculpted Landforms. Now that we understand the tools of erosion, let's look closely at the beautiful, recognizable results of this epic geological battle happening on the surface. Without a doubt, rivers are the ultimate surface sculptors. If we follow Davis's model, in their high-energy youth stage rushing down mountain slopes, rivers aggressively cut downward. They carve steep V-shaped valleys and deep gorges. As they reach flatter plains in their mature stage, their energy starts to spread horizontally, and that creates sweeping, meandering loops and those really cool, isolated, crescent-shaped oxbow lakes. Finally, in their old age stage near the ocean, they lose their transporting power. They just lazily deposit all that accumulated sediment, creating massive, highly fertile floodplains and sprawling deltas. But water doesn't just work on the surface. It also works in secret. In areas rich in limestone, mildly acidic groundwater actually chemically dissolves the rock from the inside out. This creates hidden karst topography, which means massive underground caves, dripping stalactites, and sudden sinkholes. Meanwhile, right on the edges of our continents, relentless ocean waves act as a giant physical hammer. Coastal landforms are created as these crashing waves carve out dramatic sea cliffs, flatten out wave-cut platforms, and eventually deposit the pulverized rock as sandy beaches and sheltered lagoons. And of course, we absolutely can't forget the extreme environments. In arid deserts, where water is scarce, the wind takes over.
Using sand as natural sandpaper, the wind literally blasts desert rocks into bizarre mushroom shapes and carves long ridges called yardangs, all while piling loose sand into massive shifting dunes. On the completely opposite end of the spectrum, we have glaciers, massive rivers of solid ice that slowly bulldoze their way through mountains. While a liquid river cuts a V-shape, a solid glacier plows out a massive U-shaped valley, leaving behind huge ridges of rocky debris known as moraines when they finally melt. So, from the incredibly dense iron core deep beneath our feet, all the way up to the glacial ice carving the highest peaks, we've seen how internal heat and external erosion are locked in this never-ending cycle to shape our world. The Earth truly is the ultimate tireless sculptor. Which leaves us with one pretty provocative thought to ponder today. If our planet is constantly pulling itself apart, destroying its crust, and rebuilding its surface entirely anew, what will the map of our world look like a million years from now? Thank you so much for joining me for this explainer, and remember to keep questioning the ground you walk on.